no return. And you'll notice by the time we get to the end of the run, you'll notice that it has localized itself very well. Some of the measurements still go through the walls because I'm assuming those were no returns. But just by taking these simple one-dimensional measurements, several of them at a time, and knowing the map and taking its movements, it's able to localize exactly where it is. And that's sort of a hallmark of particle filtering. You start off with a big unknown set, and eventually a whole bunch of particles go away because they're just totally inconsistent with the measurements you get. So when they get multiplied by p of z given x, the likelihood of that measurement is so small that it diminishes that particle's weight a lot, and the next time you sample, and we said this at the end, remember very low weight particles sometimes don't get sampled at all? So what happens is only the samples that are near the parts of the sensor measurements that are consistent survive, and you keep iterating. Also, remember we had the two lumps for a while there because I wasn't sure whether it was this one or that one, because it didn't have enough information to know yet. It wasn't until it went inside that room that it had that information. And this is sort of the inherent advantage of particle filtering over, say, a Kalman filter that has a single hypothesis. For those of you who've maybe heard of multi-hypothesis tracking, where you end up having multiple hypotheses, one way of thinking of particle filters is it gives me just a uniform and easy way of doing multi-hypothesis tracking. Meanwhile, at the Smithsonian Museum of American History, which is just a bigger map, bigger thing, we're going to do the same thing. One thing I'll show you here is that here the map is a little bit bigger, and in fact, if you take a look at this map, it was actually created by a robot doing what's called SLAM, where we actually used the robot to build the map. So here we have, again, the robot doesn't know where it is. It takes a bunch of measurements. These are where the actual measurements are. The robot doesn't know that yet. And this is the set of particles that survive. So you see it's clumped up a little, but it doesn't know. So it moves, takes another set of measurements, and these are the particles that survive. Now, with just two sets of measurements, almost everything else here has gone away, and we're getting a bigger clump there. Just two sets of those measurements, right? Propagate forward, take a measurement. And now you can see as it's advanced forward, it has pretty much very little ambiguity left. So again, just by taking these simple measurements, it knows where it is. How about some very simple vision? Real honest, so we're not using a depth sensor anymore. And this is about as simple a vision as you can imagine. So this is work that was done by Frank Delart, who's a professor now at Georgia Tech in our robotics and vision group. But in 1997, he was like 6 years old, it looks like. No, that's not Frank. That's some kid at the museum. Frank was doing his PhD at the time. He did something very cool. They said, you know, we've got this ceiling, and the ceiling has lights in it. If we had a map of the lights, we should eventually be able to figure out where we are by just, do we see light or don't we see light? And the way that works is you had a robot with a little camera that just looked up. All right, here's that little square. And it would just see, did I see something bright, medium, or sort of dark, right? It could just get a small number of sensor values. Or you could think of it as just taking the total value as saying, about how bright is that spot? Now, to do that, what I have to be able to do is, given being anywhere in here, I have to know what is the probability of getting that brightness in the image. So that's what this shows here, that if this was actually the brightness, this is the probability of the brightness that I would see. So the idea being, if this is the actual brightness of the state X, of the position, then this is the likelihood of what I would see. So for example, suppose I'm under a light, okay? So typically what I see is this brightish patch here, and this map is the likelihood of getting that bright measurement at these locations. And by the way, in this map, the black are the high points. So you see each one of these lights? So if I was actually under the lights, the likelihood of seeing something bright is high. Otherwise, the likelihood of seeing something bright is low. Sort of near a light, I'm going to tend to see these gray things. And when I'm far away from a light, I'm going to see mostly darkness. So those are P of z's given x. And then here's the thing running. And it's a little hard to see. You see all these red dots going. And what's happening is the robot is actually following this red line. And it comes in and it goes down. And you'll notice after a little while, it knows exactly where it is. Now it's going to turn off to the right over here somewhere. And if it hangs out in a dark area for a while, its uncertainty grows because it doesn't know exactly where it's moving in that dark area. Okay? So you're watching it and it's doing some cool stuff. What's interesting is, so we have this map of the thing. We can compare two things. The robot knows the commands that it gave to its wheels. Okay? So it knows how far it thinks it went. It also knows how much it thinks it turned. You guys have an odometer in your car? Odometer measures distance. Odometry is when you measure how you think you moved based upon how your wheels turned. If we plot on this map where the robot thinks it went based upon its wheels turning, we see something that looks like this. Okay? And the reason we know that that's wrong is that these are areas that it can't actually go through. And you see it gets sort of right, but then it sort of gets a little confused, and it's going through parts that it can't actually go through. When we add vision, and why do I say add vision? Well, we still use the odometry as the deterministic part. Megan jumped for that thing, right? So the odometry says, well, you moved a foot to the right. Okay? So we add that. That's our prediction part. So we still use the odometry, but then the measurement from the vision improves our result. Okay? And that gets us the much better result. And this is using essentially a camera just looking at a little area and saying, am I bright or am I dark? Or how bright is it? And I have a map of the ceiling. So it's pretty cool. Well done, Frank.
So you still don't believe all this particle filter mumbo-jumbo. Let's try a simple example. Here's an ant scurrying along on top of this crossword puzzle. It's one of those computer sciencey ants, so it only moves one step at a time, either horizontally or vertically. It can sense whether it's on a black square or white square, but that is it. It has no other way of knowing where on the puzzle it is. Here is a sequence of steps that the ant took. The first column is time t. The second column is its observation z, which is 1 for white and 0 for black. The final column is the action taken, or u, which is basically what direction did the ant move in. For instance, at t equals 0, the ant saw that it was on a white square, and then it moved up. At t equals 1, it observed a black square. This was the result of moving up in the previous step. Okay, the next action was moving left, and so on. Can you figure out where the ant is at t equals 5? Mark the appropriate checkbox, or boxes if you're still unsure. Okay, let's see how a very simplified particle filter can help us estimate the ant's position. Initially, at t equals 0, we have no idea where the ant is. So we might as well assume that it is in one of these squares, any one of them. This is our initial prediction. Now the observation says that we are on a white square. The likelihood of us getting a white observation when we are on a black square is really low. So in our simple case, we get rid of the particles in the black squares. You can think of this as a correction. Okay, now we see that the action taken was move up. So we take our entire distribution of particles and we shift the whole thing up, like that. Any particles that went outside the valid area are discarded. Now this is our best guess or prediction at time t equals 1. This time we see that the observation is black. So all the particles on white squares are basically inconsistent with the observation. As before, we get rid of them. Alright, our next step at t equals 1 is to move left. Observation at time 2 is white. So we get rid of all the black particles. Next, we move up. Interestingly, all the particles on the board are consistent with the observation. At step 3, we move up again. Now the observation at step 4 is black. So we get rid of the white particles. Now we're left with only 3. Well, from here we move right. And the observation is white, so we get rid of the one black particle. And that's it. We're left with 2 possible positions for the ant. Since we don't have any further information, that is our best guess. Are you wondering where the ant started? Well, it could have started here at t equals 0. Move up, see black, move to the left, see white, move up again, white, move up, black, move to the right, and you see white. But that's one possible path. The other starting point could have been down at the bottom here. Same thing, move up, black, left, white, up, black, right, white. So, particle filters, useful, aren't they?
Before ending this lesson, I want to talk about a couple of practical considerations of particle filters. And the first one involves sampling. As you can imagine, sampling is really important, okay? Because I have this set of samples, and every step I have to generate a new set of samples. So I have to resample it. I go grab a sample where the probability of pulling out that sample for state X is proportional to the weight of that sample. And typically, I'm doing this a constant amount of time, so n times. So I'm using 1,000 samples, 10,000, however many samples, I'm doing that every time. We'll talk, actually not today, but next time. That number can get kind of big if your state space gets large, so being able to sample effectively or efficiently or less often is kind of important. So I want to talk about resampling a little bit. What we have here is an outer ring, okay, where the idea is that the arc length of that ring is proportional to the weight. Okay, so, you know, W1 is small, W2 is bigger, W3 is huge, etc., whatever. And these are all the weights, right? So you can think of sampling as following. I just randomly pick a direction, and if I hit W3, I'm going to take sample number 3. So that'd be my first sample. All right, do it again. If I hit Wn, I pull out the nth sample. And basically, I have to keep doing that n times, right? So it's like a roulette wheel. I spin the roulette wheel n times, and I have to figure out where I land. And that figuring out is actually a binary search, so that's log n, but I do that n times. So it's an n log n operation. So that's kind of, it's not awful, but it doesn't scale linearly with the number of samples you use. It goes up by n log n. It turns out there's a cute little trick that you can use that is, instead of like a roulette wheel, is more like a wagon wheel. And the way it works is this. So let's suppose I have n samples. I can make a set of spokes that are 1 over n full rotation around. So here I've got 1, 2, 3, 4, 5, 6, 7, 8, right? So each one is 1/8 of an arc. And what I can do is I can randomly put it down someplace, and if I've randomly done it, then I can just read off for each one of these spokes which W did it hit, okay? And in fact, the starting weight, right, I can just start at some random one here, and I see what W am I at, and I go to the next one, and I see, did I pass a boundary? If so, then I'm at the next W, and likewise. So what's nice about that is that's done in constant n time. And it's sometimes called stochastic universal sampling, systematic resampling. The nice thing about it is that it's a linear time complexity. You know, if you do 10,000 points, it takes you so long. If you do 20,000 points, it takes you just twice as long. All right? And it's very easy to implement. In fact, it's so easy to implement, let me show it to you. So here I'm showing you that actual wagon wheel algorithm that we just talked about, this systematic resampling. You start off with no new samples, and you build the C's are going to represent the outer ring, the cumulative distribution function. And essentially, each one represents the one before it plus the extra new weight. Right? So you start off at the first weight, and then C2 is the sum of W1, W2. C3 is sum of W1, W2, W3. That's that outer ring. Okay? You can think of it that if it goes from 0 to 1, because everything sums to 1, then the C's are sort of how far, what percentage around the clock have you gone. The next thing you do is you have to pick. Remember I told you you have to sort of randomly throw down the wagon wheel to start with? Well, if the wagon wheel has 8 spokes, the first spoke has to go somewhere between 0 and 1/8. That's what this is right here, right? N to the minus 1, maybe I should write it as 1 over n. That's the offset. And then what you do is you go around the outer ring seeing, wait, did I pass my offset yet? As soon as I've passed it, that's the CDF part that I'm in. So just drawing that on here, if this is my first one, right, and this is where it starts on the outer ring. I say, did I pass it yet? I say, nope. Okay, did I pass it yet? Yes, I did. So this first spoke landed in W2. Then I just go to the next spoke, and I say,